So let's start with metallic bonding, because this is fundamentally different than the other types of chemical bonding you probably learned in your introductory chemistry class, if you were fortunate enough to have taken that. So there's ionic bonding. This is where electrons are transferred completely from one atom to another. An example of this is table salt, sodium chloride. So in sodium chloride, sodium gives the electron to chlorine, both become ions, and the positive and negative ions attract each other. So they're strongly bonded. In covalent bonding, like water or carbon dioxide, electrons are actually shared between the specific pairs of atoms. This often occurs with nonmetals, and the bond is localized between those two atoms. In metallic bonding, this is a little bit different. In both the metal and the valence electrons, which are the outermost electrons, they're not transferred from another atom and they're not shared between atoms. The electrons kind of belong to the entire collective of electrons in that piece of metal. So if you imagine a copper wire, every copper atom has 29 protons in the nucleus and 29 electrons. 28 of those electrons are tightly bound to the nucleus in its inner orbit shells, if you think back to the Bohr's model. But there's the 29th electron is the single valence electron in the outermost shell, and it's given up to the shared electron pool or the electron cloud. So if we multiply that one electron by the number of copper atoms in a wire, if we just look at 1 cubic centimeter, this is approximately 8.5 times 10 to the 22nd atoms. So basically 85,000 billion atoms. So all of a sudden that one tiny electron becomes very significant in this electron cloud. So each one of those copper atoms contributes one free electron. So in this enormous sea of free electrons, there's a lot of names for this. This is electron cloud, electron sea, or free electron gas. It kind of flows through and around the positive copper iron cores, which sit in a regular crystal lattice structure, if you look at the atomic level. So this big electron cloud goes through the whole metal. And the electron sea model explains immediately why metals have properties that they do. So some of the properties of metals, right, are electrical conductivity, which are the free electrons, which respond to any applied electric field, and they flow through the metal as electric current. So the more free electrons per atom and the more freely they move, the better that metal is conducting those electrons. These metals also often have good thermal conductivity. So the same free electrons that carry electrical current also carry thermal energy. And this is why metals feel cold to the touch, and they can conduct heat very rapidly. And this is why copper pots heat evenly and quickly. Another property is malleability and ductility. Because the electrons are delocalized and they're not tied to specific directional bonds, the metal ions can slide past each other when force is applied without breaking the bonding. So the electron sea simply accommodates the new arrangement. And this is why you can hammer copper into a thin sheet or draw it into a wire without it shattering. So another property of metals is that metallic luster. And this is due to free electrons interacting with the incoming light across a broad range of frequencies. And so they kind of absorb and re-emit it. And this is why metals are shiny and the electron sea reflects that light efficiently. So all four of the properties of the metals that I just mentioned, conductivity, thermal conductivity, malleability, and luster, they all are a result of that delocalized electron sea.